Bismillahirrahmanirrahim. Good afternoon, everyone. Today I will talk about the electric resistance effect in perovskite oxide. This is my lecture title because I will discuss that. This will be something like similar to me on the next Friday at 27th of June. Let's go directly to the outline to discuss some important things. This will be something like map to me. I will use many simple, not simple, actually it's critical points to kind of explain to the all audience my idea about the electric resistance. For example, I will start from the manganite oxide properties, how this section is widely dealing with many properties. One of them is electric resistance, as my today lecture title. And after that, I will explain the relation in the temperature resistance curve. What is the Curie temperature, what is the isolating material transition temperature, and many things like that. The difference between after this critical point and before. The double exchange mechanism and the giant Taylor effect, because all of them is very important two methods to us. We use it in electric resistance in manganite. After that, the experimental research by taking many components from many articles. I put it all of these articles' name. The last slide, like sources slide. Now let's start. Now, like we know, the original form to the perovskite oxide, not dioxide. Here I have a mistake. Oxide, perovskite oxide, because dioxide that's mean a number of oxygen. Perovskite oxide is AbO3. All of Ab are alkaline and 3 atoms of oxygen. Actually, here at this lecture, we depend on this form, lanthanum manganite O3. It's another version belong to the AbO3. When A is lanthanum, the component is lanthanite. When B manganese, the component is manganite. It's important, simple but important. Now, like I said at previous slide, the manganite oxide has many properties like electric properties, electric resistance, manganite resistance. But here our lecture title is electric resistance properties, because that I will focus on the second one. Here, let me draw something. Here it's the resistance temperature curve. The temperature Kelvin at Kelvin unit at the x-axis and the resistance at the y-axis here at ohm centimeter. Now, let me explain what is the isolating metallic transition and what is the Curie temperature and what the difference between them, which one will be in which side dealing with which properties. Actually, isolating metallic transition temperature dealing with the isolating metallic things, and the Curie temperature dealing with ferromagnetic, paramagnetic metals. Here, let me draw this thing, this curve to put another opportunity to make this be easier. Yes, this pencil, this color with this line, that's right. Here, for example, this curve here is isolating. It's delta resistivity divided on delta T. It's bigger than 0. That's mean here is the isolating field, isolating area. But after crossing this point at the top, something will be, this isolating will be metallic after cross this critical point at the top. And here, by measuring the temperature at the temperature line, we can say here approximately 120 Kelvin. That's mean here the isolating metallic transition temperature equal 120 Kelvin. After this point, the metal will act like like a metal. That's mean here delta resistivity divided on delta temperature is smaller than 0. The same thing with the Cure temperature here. At this point, we can say it's a Cure temperature. What does mean here? It's paramagnetic. Here will be ferromagnetic. That means here the magnetization properties, it's more than the first area. Okay, that's it. This the resistance temperature Kelvin curve. Sorry, resistance temperature curve. And we will apply different amount of current. Start from small amount until a huge amount, comparing with the starting point. And after that, we will try to determine the resistance. And let's take a look to the resistance if it will increase or decrease. And his relation, the resistance relation with the current, the current will increase with decreasing the current, or reverse bias, or different situation. Let's keep going. Let me delete all of that. Come on, take a look. Now, before keep going to explain the double exchange and Taylor theorem effect, all of these we use it to explain the electronic interaction in the manganites, By using them, we can explain the electrical manganites or manganite oxide and the perovskite oxide. Now here, double exchange mechanism at 1955, it's proposed by Zener. Zener proposed it. Here, like we know, we have two states, too late opportunity to electron to sit in lines like that. The first one, T2G, it's the lower one, AG is the upper one. T2G have 3 lines, and here like I said before, at manganites we have 2 different charge, 3, 4, and 3 plus and 4 plus. Here at 3 plus, that's mean I have 4 electrons, because at full situation, we have 7 electrons. Here, when I have 4 electrons, that's mean I have 3 something like holes, because that we say 3 plus, that's mean I have 4 electrons. And here 4 plus, that's mean I have 3 electrons. That's mean the upper one, the upper shell, the upper state is full, totally it's empty. And between them is the oxygen, like here. The oxygen will be something like bridge. It will give the opportunity to electron from jump from this EG, upper EG at the Mn3 plus to forward the manganese 4 plus by using the oxygen like a bridge. Here will be like that. At the directions, we will follow the Hans rule. No way two spins will be at the same direction. One of them upper, the second of them will be at the down direction, like that. And here, after the oxide is created, the angle between them, between oxygen and manganite, will be smaller than from 180 to be smaller than 180 here. Here, let me use the pencil. Here, some different how I can use the pencil from here. Yes, some difference at the angle here will be smaller than 180, because that. Now let's do a simple comparison between the double exchange and super exchange. Actually, here, by using the hand rule, the electron will jump from the 3 plus to 4 plus by using the electron like a bridge, and after that keep going. Some similarity with the doping when was inject the electron and will keep jump from step to step. The same idea, some similarity with it. We'll jump from Mn3 to the oxygen between them, and after that another jump to the Mn3, 4, and the charge will be continuously changed. Here ferromagnetic, but here antiferromagnetic. Here at superchange, the direction will be totally at the next side will be totally different, because all of them will be to downside at some difference, a huge difference with the first side, with the left side. And here the direction will be with this left side, hand side will be different. Here it's super exchange, here it's the double exchange. Here, this model is more resistivity than the super exchange. We talked about the double exchange. It's more resistive than super exchange. Restrictive, the double exchange is more than restrictive than the super exchange interaction, and requires the presence of ions of the same element, but in different valence state. Here it's important, but in different valence state. Let's take a look, another look to the next slide here. Let's start to explain the Jane-Taylor theorem. It's important because all of them try to explain to us the magnetic properties in the manganites and another properties, another characteristics. Jane-Taylor theorem, any complex occupying an energy level with electronic degeneracy is unstable. Against what? Against a distortion that removes the degeneracy in the first order. The most important thing in the Jane-Taylor theorem, like we know, like I said at the previous slide, we have two levels, T2G with at approximately 3 electrons, and EG with 1 at Mn3 plus. Here we can say, we can divide these three lines to two groups. The first one, dxy, dyz, and the last one will be between them some distance, not small distance, approximately, or if you do comparison with the first image, some different, but I use another way to put these names, these symbols in my mind. I will start from here to say dxy, dxz, dyz, dxy, dxz, dyz. And after that, now I'm talking about EG level. Here, dx square minus dy square and dz square will be something like that at the introduction, at the Jane-Taylor theorem. And like I said before, any complex occupying an energy level with the electronic degeneracy is unstable. Against what? Against the distortion that removes the degeneracy in the first order. Here, the author said to us, Mn 4 plus with no distortion, but here, like we say, some different at this image from Mn3 to after distortion, some different distance between these lines at the middle be smaller than, and this line be longer than. Here, let's take another important note about Jane-Taylor effect. Now it's not necessary to write Jane-Taylor effect. All of you know what that means. It's an important mechanism of symmetry. Breaking the molecular, that means not take a scan from the surface. No, we will take another deeply idea, deeply look, deeply information by breaking the molecular or the solid state system. Here inside the John Taylor effect, we have high spin, low spin theory. It's important. Let me explain it. For like we know, we have two levels, T2G and EG. 2TG at the down side, at upper side will be EG. For example, we have 5 electrons. I will say 1, 2, 3, 4, 5. But here the situation is different at low spin. And we can say high field or low spin, the same meaning. We'll say 1, 2, 3, 4, 5 electrons. But let's take another example. If we have 7 electrons, what we will do? 7 electrons, I will say 1, 2, 3, 4, 5, 6, 7. Okay? But here the situation is different. Why? Because 1, 2, 3, 4, 5, 6, 7. Okay? It's a difference between high spin and low spin. According to the Jane-Taylor theorem, any molecule or complex ion in electronically degenerate state, any molecular or complex ion in electronically degenerate state will be unstable. Will be what? Will be unstable relative to configuration of lower symmetry in which the degeneracy is absent. In which the degeneracy is absent. That's mean here we have a condition. Now, let's take a simple look about the electric resistance before keep going to go to the experimental details. Electric resistance is the change in electrical with the current, some change with the electrical and the current by apply different amount of current and something like that. I will explain that by using some uploads to make this idea be better. Electric resistance was observed with 3 things. The first one is the bulk polycrystalline bulk manganite, thin film manganite, and the last one is single crystal. That's mean bulk polycrystalline, we can say thin film, and single crystal manganite. Here, the first slide talked to us about the experimental research. Here, we have to actually the same component, but with different concentration. Here, 0.6, 0.55, 40, 45, 0.45, sure. Here we have 2 plots explained to us. We apply, or the author, they apply different amount of current, start from 0.1 microampere until 50 microampere. Start from the black one, that's mean here, the bigger one at the top. Okay? Increasing, and after that, when across the 130 start to, or when across this high point start to decrease again until 200 Kelvin. Here we have important thing. When increase the current, the resistance is decreases. Why? Because here at the first 1.1 milliampere, it's more than 80 ohmic centimeter. And at the last, for example, 15 milliampere, that's mean we increased the current until 50 milliampere. We know the resistance is less than 60 ohm centimeter. Here at the X equal 0.45, starts from 0.1 until 50 milliampere. Here at the situation, the resistance is decreasing to, but it's less than the first image, because some simple difference between resistance at 0.1 milliampere and at resistance with 50 milliampere, but we have decreasing but less than the first image. This is the article title at the last H slide. Here, this image illustrates to us the difference between the previous two plots. Here at concentration X equal 0.4, from 1 decreasing until 0.7 here at 40, and here at concentration equal 45, decreasing starts from 1 until 95. That's mean we have decreasing, but not like the at previous plot. Here it's important why we have difference like that, because the contrasting homogeneity of these two compositions. Here another sample from another article. Here, from room temperature until approximately 0 Kelvin. Here we apply different amount of currents from 0.1 milliampere until 7 milliampere. From the black one, this one at the top, and after that decreasing suddenly like that. Here less than 50 ampere, here decreasing, and after that increasing. Not too much, little bit, but decreasing, and after that increasing. All of these to all of this amount of current under 50 Kelvin. Okay, here if we plot the current, we will say all of these colors will take will cross from the 0 point, from starting point, and act to ohmic behavior to be all of these like lines. Here let's talk about at the high temperature and out of plan. This figure shows to us the measured with temperature. Here at the top, here the isolating temperature, transition temperature, isolating metallic. That's mean here it's isolating his as metallic. And here by using the IV curve, we will say all of these colors will not follow the ohmic behavior anymore, because here some curves at the minus area and positively area. Here start from 0.5 microampere until 1000 microampere. Here, when increasing the current, the resistance is decreasing. Here it's important by take notes, by take deeply, plot deeply, care deeply, idea from the constructor, from this manganese, by broken this manganese or broken the solid state, to take deeply idea. This idea is what? By using the magnetic force microscopy, it's a way, it's a method to can measure the atoms limits, the distance between the atoms, the quality, the constructions of these atoms, because something like that here we have many metallic atoms, but between them we have isolating metallic. Let me keep going here. The current doesn't change the shape of the ferromagnetic domains. The current doesn't change the ferromagnetic domains, but a few small ferromagnetic, microscopic ferromagnetic domains appear at critical regions. Critical regions because by applying the current, all of these atoms will try to create a bridge between them to bridge large neighboring ferromagnetic domains. Here, this is very clear to us and benefit. By take a look to image like that, we have distance between these two atoms by zero current. And here, by increasing the current, this distance will try to decrease. By using the current more, this distance approximately disappear at amount like that. The distance between these two atoms approximately, totally, not approximately, totally disappear to create something like a bridge. What that's mean? That's mean the metallic properties will be stronger than the magnetic properties, magnetic characteristics will be stronger than, because after reach amount of current like that, this isolating atom will act like another metallic atom. Here, figure A showed to us the dependent resistivity of this constructor. Here, at this result of current at 2, some increasing, after that decreasing like that. But when warming it from approximately 0 Kelvin to 300 Kelvin will act like that. But after that, when cooling it from 300 until approximately 0, we will note some hysteresis phenomena between all of these colors to all of these amount of currents. And here we can say here the resistance was approximately 1,000, but here approximately maybe 10 ohm centimeter. That's mean huge decreasing between these two amounts. That's mean by increasing the current, the resistivity is decreasing. Here we have 3 critical points. Approximately, the first one is approximately 80 Kelvin. After more than 50 Kelvin, the hysteresis will start to appear. Until 170, the hysteresis will disappear to be overlying all of these colors with together. Here is the resistance temperature curve. Here, like I said before, all of these currents are continuous current, but the last one is the pulse. Here, it's more than 150. All the hysteresis phenomena will start to disappear until warming or cooling. Here, some huge amount between them, and all 3 cases, the same was called from room temperature 300 Kelvin to the measuring. Here, by increasing the current, the resistivity is decreasing, like I said before. Here, from 0 to 300, it's warming, and here it's cooling. Here, at 100, more than 150 Kelvin, the change of the resistivity almost recovers the original value after the current cycle, like I said before. Here, another simple, it's here are these 2 plots. The hysteresis phenomena is very clear here because a huge distance between all of these, the original one and the upper one. Here, by apply different amount of current, start from 1.1 milliampere until 13 milliampere, from approximately 0 to 200 Kelvin. Let's start from the 0, 1, the black one from here, and after that, the red one, the green one, and keep going toward the 0 Kelvin. All of these at warming and cooling, we have a huge different distance of hysteresis phenomena. And when apply one amount of current, 11 microampere, we have two hysteresis phenomena. Here, at the sample with the electric resistance with the temperature curve, we have the hysteresis by warming and cooling. Here, with another sample, here as cooling, here warming. All of these hysteresis is start at more than 50 Kelvin. At approximately 150, this phenomena is disappeared totally. Here, the resistivity and temperature. Magnetic and electrical transport properties of the components. Like I said before, I put it all the article's name below every plot, every figure. That's it, the summary when we once talked about the original form about cations AB and O3, and another source ABX3, at the same actually, as the general form that perovskite oxide, not dioxide. I will fix it. The original form, or we will depend on form like that, not the original. The original one is here. We will depend on containing like that, lanthanum, manganite, O3. The manganese oxide properties, like we talked about it, and many properties like electrical properties, electric resistance properties, magnetic and magnetic resistance properties, but we was focused on the electric resistance because it's my seminar title, and I explained the temperature curve, temperature resistance, at what is the isolating metallic transition temperature and what the Q temperature, when will be isolating, when will be metallic, when will be ferromagnetic, when will be paramagnetic, and the double exchange mechanism. We used it to can study the magnetic properties of the perovskite oxide and the Joule-Taylor effect. All of these are important two methods to calculate, to can study, to can determine the characteristics about magnetic oxide, perovskite oxide. And here is the magnetic force microscopic. It's a theory to can take a deeply idea, a deeply information about the atoms, about the atom limits. Here, electric resistance was observed at three situations: polycrystalline at bulk, thin film, and the single crystal. The relation between temperature, current, and resistance, when was applied the current, the resistance is decreased, and the temperature, some difference between the temperature amount. And the last thing I explained it was the hysteresis phenomena when I cooling the component and warming the component. We watching some different about the amount, about the curve, but not at all the curve, but at some point it's the start, at some point it's the second. That's it. The source, the references, I depend on 5 or 6 articles. You can take a look, you can take a look to all of this information, all of these articles. Thank you about your watching or listening. Have a good day. I wish it was helpful to you and to me.